Integral test and P-series. Integral test. If f is positive, continuous, and decreasing for x greater than or equal to 1, and if the a sub n equals f of x, then the sum from n equals 1 to infinity of a sub n and the integral from 1 to infinity of f of x dx, they either both converge or both diverge. So if you can get the integral to converge, then the series converges. And likewise, if the integral diverges, then the series will diverge. If the series converges to s, then the remainder, r sub n equals s minus s sub n, or in other words, the exact value minus the estimate, is bounded by 0 is less than or equal to r sub n is less than or equal to the value of the integral. So the value of the integral will be the maximum error. Determine whether the following series converge or diverge. So here's the a sub n. There's a sub n, and a sub n in this case is going to be the same as f of x, which is x over x squared plus 1. So now we're going to do the integral on this, and if the integral converges, the series converges. We have the limit as b approaches infinity of the integral from 1 to b of x over x squared plus 1 dx. And we're going to do the integral here by u substitution. We'll let u equal x squared plus 1. Du is equal to 2x dx. And then we don't have a 2 up here. We have 1/2 du is equal to x dx. Now we have the limit as b approaches infinity of the integral from 1 to b of, we have 1/2 du over u. The x squared plus 1 is the u. And that's going to go to the limit as b approaches infinity of 1/2 times the natural log of the absolute value. The integral of 1 over u is natural log. And but u is x squared plus 1. So we have x squared plus 1, and we're evaluating from 1 to b. That's the limit as b approaches infinity of 1/2 times. We have the natural log of the absolute value of b squared plus 1, and then minus the natural log of the absolute value of absolute value of 2. When we plug infinity into this right here, we'll have the natural log of infinity squared plus 1, which is infinity, and natural log, it shoots off to infinity. So as x approaches infinity, shooting off to infinity, this all equals infinity. So we say diverges by the integral test. There we go. Let's look at b. We have the limit as b approaches infinity of the integral from 1 to b of 1 over n squared plus 1. Actually, if we're going to go f of x, then that's x squared plus 1 dx. And that's the limit as b approaches infinity of, that's going to be inverse tangent of x from 1 to b. We have the limit as b approaches infinity of inverse tangent of b minus inverse tangent of 1. The graph of inverse tangent looks like this. We have negative pi over 2 to pi over 2, and these are the asymptotes. And then here is inverse tangent. So as x approaches infinity, inverse tangent is leveling off to pi over 2. So when we plug infinity in, we have inverse tangent of infinity minus inverse tangent of 1, and that's pi over 2 minus pi over 4. We have 2 pi over 4 minus pi over 4, which is pi over 4. So this converges, the integral converges to pi over 4. So we say converges by the integral test. Approximate the sum of the convergent series, this series right here, by using 6 terms. Include an estimate of the maximum error for your approximation. Let's get the first 6 terms. We have 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th plus 1 over 4 to the 4th plus 1 over 5 to the 4th and plus 1 over 6 to the 4th. I've spared you all the excitement of watching me type this in, but here we have 1 over 1 to the 4th, 1 over 2 to the 4th, 1 over 3 to the 4th, and so on. And the estimate is 1.081. So we have 1.081. It says now include an estimate of the maximum error for your approximation. Let's go back up to the integral test. It says if the series converges to S, then the remainder, R sub n equals S minus S sub n is bounded by 0 to the integral of f of x. But notice that we want the remainder after the 6th term. So 0 is less than or equal to R sub 6 is less than or equal to the integral from 6 to infinity. So we need to go from 6 to infinity if we're finding the 6th degree error. So we have the limit as b approaches infinity of the integral from 6 to b of 1 over x to the 4th dx. Now that's really x to the negative 4, so when we integrate we'll have negative 1/3 x to the negative 3rd. So now we have limit as b approaches infinity of negative 1 over 3x to the 3rd evaluated from 6 to b. That's the limit as b approaches infinity of negative 1 over 3b to the 3rd and then minus a negative, which is plus 1 over 3 times 6 to the 3rd. Now when we put infinity in here, this piece is going to go to 0 and we're left with 1 over 3 times 6 to the 3rd. 1 divided by 3 times 6 to the 3rd. And that's equal to, the maximum error is 0.00154. P-series. A series of the form, sum from 1 to infinity of 1 over n to the p, that's equal to 1 over 1 to the p, 1 over 2 to the p, 1 over 3 to the p, and so on, is called a p-series where p is a positive constant. For p equals 1, the series n equals 1 to infinity of 1 over n to the p is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. This is called the harmonic series. What values of p would cause this series to converge and to diverge? Well, let's let p equal 1. That means this is the series that we have. N equals 1 to infinity of 1 over n. Let's use the integral test to decide whether this converges or not. We have limit as b approaches infinity of integral from 1 to infinity of 1 over n. That's limit as b approaches infinity of natural log of absolute value of n from 1 to b. And that's the limit as b approaches infinity of natural log of the absolute value of b and then minus natural log of the absolute value of 1. Now this is 0, but if we're going to plug infinity into this, actually plugging it in, so natural log of infinity, that's shooting off to infinity, so this diverges. The harmonic series diverges. Let's look at when p equals 1.1. We have the limit as b approaches infinity of the integral from 1 to b of 1 over n to the 1.1, and I guess we're going to do dn here. Now that's really n to the negative 1.1, so when we add 1 to do the integral, we have n to the negative 0.1 and then times negative 1 over 0.1. We have the limit as b approaches infinity of 1 divided by 0.1 is 10. which means we're going to have negative 10 over n to the 0.1, evaluated from 1 to b. So we have the limit as b approaches infinity of, we have negative 10 over b to the 0.1, and then plus 10 over 1 to the 0.1. And when we plug infinity in for this b, the b becomes, or the denominator becomes infinity. That means this is going to be 0, and we end up with 10. So this one converges. This one converges by the integral test. On the last one, p is 0.9. We have the limit as b approaches infinity of the integral from 1 to b of 1 over n to the 0.9 dn, or we could make those x's. This is really n to the negative 0.9, and then when we add 1 to this, we get n to the 0.1, and then we have 1 over 0.1 out front. So this becomes the limit as b approaches infinity, and this is the integral right there. We have 10 n to the 0.1, and we're evaluating from 1 to b. That's the limit as b approaches infinity of 10 times b to the 0.1 minus 10 times 1 to the 0.1. And then when we plug infinity in here, that's shooting off to infinity. This one is infinity, and it diverges. And that will happen for any value of p that's less than 1. So bigger than 1, we converge. Less than 1, it's going to diverge. So given the p series, if p is equal to 1, diverges, diverges, there we go. If p is greater than 1, then it converges. And if p is less than 1, then this series diverges. Let's look at the last example. This series is equal to the sum from n equals 1 to infinity of 1 over n to the 2 halves, that's really n to the 1, times n to the 1 half. That's equal to the sum from n equals 1 to infinity of 1 over n to the 3 halves. 3 halves is greater than 1, so we say converges by p series.